Dear students, today I am going to discuss about the steady state analysis. Previously I discussed about the transient analysis, its specific parameters discussed in the classroom. Now I will discuss about the steady state analysis and steady state error analysis. All these things we will discuss now. Error function E of s, error transfer function E of s by R of s is equals to 1 by 1 plus g of s into h of s. This is error transfer function. Error transfer function. Here E of s is the error signal, R of s the input signal, and it is equals to 1 by 1 plus g of s and h of s. Here the h of s is the unity feedback transfer function. That is a negative unity feedback transfer function. Is equals to h of s is equals to 1. So E of s is equals to 1 by 1 plus g of s into R of s. Okay. Here the error E depends on the input signal and forward path transfer function So where g of s is the negative unity feedback transfer function, g of s and h of s is equals to g of s, that is k into s plus z1 into s plus z2 etc. by s power n s plus p1 s plus p2 etc. Here the transfer function is in the form of pole zero form. Representation, where n is 0, 1, 2, 3 etc. So n represents the type of the system. If n is 0, type 0 system. And at the same time, the same transfer function can be represented in another approach, that is s t z1 plus 1 s t z2 plus 1 etc. s t p1 plus 1 into s t p2 plus 1 etc. into s power n. Again, just before I told you, n is a type of the system. This is the time constant form representation. Time constant form. So transfer function can be expressed in two ways here: pole zero form representation, time constant form representation. That is, this is the way g of s is equal to dependent, where n is 0. N is 0 in the sense type 0 system. N is 1, type 1 system. N is 2, type 2 system. Like that. Here type 0 system means g of s is equals to k into s plus z1 into s plus z2 etc. by s power 0 into s power p1 s plus p1 s plus p2, like that. So type 1 system, g of s is equals to k into s plus z1 s plus z2 etc. s power 1 s plus p1 s plus p2, like that. And type 2 system is g of s is equals to k into s plus z1 into S plus Z2 etc. by S power 2 into S plus P1 S plus P2 etc. Here the first one type 0 system. So here S power 0 means type 0 system. No pole at origin. No pole at origin. Type 1 system, one pole at origin. And type 2, two pole at origin. Two pole. So no integrator, one integrator, two integrators. Means two integrators means two poles at origin. One integrator means no one pole at origin. No integrator means no pole at origin. Now we'll discuss about the steady state error. Steady state error. Type 0 system. Type 0 system. So to find the steady state error of a system using final value theorem. Suppose E of S is the steady state error signal. EFS is the steady state error signal. Want to find the steady state error value using final value theorem, that is ESS is equals to limit S tends to 0 S into E of S. This is the function you have to. This is the final value theorem representation. Final value theorem, that is ESS steady state error is equals to limit S tends to 0 S into E of S. What is E of S? Where is E of S? Is R of S by 1 plus G of S H of S. So H of S is negative unity feedback system. So that the H of S is 1 is equals to R of S by 1 plus G of S. Here type 0 system input R of S is equals to that is a unit step input. R of S the unit step signal that is R of S is equals to 1 by S. Now find the steady state error ESS is equals to limit S tends to 0 S into 1 by 1 plus G of S into 1 by S. This S cancel, that is also equals to limit S tends to 0. Okay, sorry, 1 by 1 plus limit S tends to 0 G of S. So limit S tends to 0 G of S is equals to, this is a type 0 system. Limit S tends to 0 is K into S plus Z1 S plus Z2 etc. by S plus P1 S plus P2 etc. This substitute S is 0 in this is equals to K into Z1 Z2 by P1 P2. Z1 Z2 is a constant, P1 P2 is become another constant K. This is called, it is called as a KP means KP is limit S tends to 0 G of S. G of S, where G of S is the type 0 system. So Kp called as a position error coefficient or constant, CIENT. Kp is equal to positional constant. That is, this is the positional constant. This positional constant is equal to, finally, error ESS is equals to 1 by 1 plus K, that is also equal to 1 by 1 plus Kp. This is Kp, K. So it is a finite value. Error as a finite value. Next, same type 0 system. Input signal R of S is a ramp signal, that is 1 by SS square. Now error ESS is limit S tends to 0, S into E of S, that is limit S tends 0, S into R of S by 1 plus G of S, that is limit S tends 0, S into 1 by 1 plus G of S into 1 by SS square, that is, which is equals to limit S tends to 0, 1 by 1 plus G of S into 1 by S. This S 1S and to cancel become like this. Now limit, that is limit S tends to 0, 1 by S plus limit S tends to 0, S into G of S. Okay. Limit 0. So here substitute S is 0 here, that is 1 by 0 plus limit S tends to 0, S into G of S, S to G of S. Okay. So limit S tends to 0, S into G of S is Kv, called as velocity error coefficient. Now, so this Kv is called velocity error coefficient. Limit S tends to 0, S into 1 plus, S into Z1, S plus Z1, S plus Z2, etc. Some K into, S into K into this one by S plus P1, S plus P2, etc. That is S power 0. But because type 0 system, here substitute S. So this value is equals to K by this is limit S tends to 0, S into K into Z1, Z2 by P1, P2, like that. S power 0 is equals to 1. So it become, substitute S is 0, its value is equals to 0. Kv is equals to 0. Kv. What about the steady state error? Steady state error S is equals to 1 by here, this is equals to 1 by Kv. Kv is equals to 0 is equals to infinity. And what you understand here? Here type 0 system for ramp signal, for type 0 system, input is ramp signal, steady state error is equals to infinity, velocity error coefficient is equals to 0. Previous case, type 0 system, input signal is unit step. So position error constant is some finite value. Yeah, steady state error is equals to 1 by 1 plus kp. So it is also a finite value. Whereas here ramp signal for type 0 system, input velocity error coefficient is equals to 0. Steady state error is equals to infinity. Now type 0 system, input signal RFS is parabolic signal, that is parabolic signal 1 by SS cube. Now find the steady state error, same as previous. ESS is equals to limit s tends 0 s into ES E of S, that is equals to limit s tends 0 s into E of S R of S by 1 plus G of S. Already you know that H of S is unity feedback, that's why I am not considered 1 by 1 plus G of S directly written here. Again same as written here, limit s tends to 0 s into 1 by 1 plus G of S into 1 by SS cube. Finally, limit s tends to 0 1 by 1 plus G of S. Here 1 is in numerator s power 1, denominator s power cube. So numerator cancelled, denominator becomes 1 by s square, that is 1 by s square. 1 by s square. Now 1 by 1 limit which is equal to limit s tends to 0 1 by s square plus s square G of S. That is same thing as limit s tends to 0 s square plus limit s tends to 0 s square into G of S. Now limit s tends to 0, substitute s is here, so the term 0 plus limit s tends to 0 s square G of S, that is equals to limit s tends to 0 s square G of S, that is equals to 1 by K A, where K A is limit s tends to 0 s square G of S is called acceleration error coefficient. Now you find the steady state error Ka for this one, limit s tends to 0 s square into G of S some k into s plus z1 s plus z2 by s plus p1 s plus p2 etc. Substitute here, it becomes is equals to 0. K is also 0. Steady state error ESS is equals to 1 by Ka. 1 by Ka is equals to 1 by 0 is equals to infinity. So steady state error for the for type 0 system, for ramp signal also is infinity. In previous case, for ramp signal also steady state error is infinity. For unit step input only, it has some finite value. Now from this, what you observed here, so Kp is a position error constant, Kv is a velocity error coefficient, and K is a acceleration error constant. Error coefficients have determined from the error coefficients of the steady state errors are determined. So steady state error for 1 minute. Steady state error steady state error, and error coefficients, Kp, Kv, and Ka. But here type 0 system, unit step input, unit to step, unit ramp, unit parabolic, So type 0 system, steady state error, type 0 system. What is that one? 1 by 1 plus Kp. This one infinity. This one is infinity. Similarly, you find type 1 system for type 2 system. Determine the steady state errors. Okay. Here, remind here, Kp is equals to limit s tends to 0 g of s, and Kv is equals to limit s tends to 0 s into g of s, and Ka is equals to limit s tends to 0 s square g of s. So the error constants, error coefficients first you have to determine, later you have to determine the steady state error for type 0 system, type 1 system, type 2 system, subject to unit step in, unit ramp input, and parabolic input. Clear? So this is about the error steady state analysis. You have to complete the type 1 system and type 2 system steady state errors subject to unit step, unit ramp, parabolic inputs. So this is about the steady state analysis, steady state errors where you have to find out. Here the error coefficients, Kp, Kv, Ka describe the ability of the system to reduce the or eliminate the steady state error. The error coefficients Kp, Kv, Ka describe the ability of a system to reduce or eliminate the steady state errors. So I'll stop here. You please complete unit step input for type 1 system steady state error, unit ramp input for type 1 system steady state error, for unit parabolic for type 1 system steady state error. Before you have to determine Kp, Kv, and Ka. After that, unit step input for type 2 system steady state error, unit ramp input for type 2 system, unit ramp input type 2 system steady state error, and again unit parabolic error for type 2 system steady state error. You have to complete and understand the whole steady state error analysis of the system. The error coefficients describe the ability of system to reduce or eliminate the steady state errors. So thank you. If you have any doubts related to steady state errors, please ask me. I'll respond to that one.